Alright, so now we are on to start what are called the study of eigenvalues and eigenvectors. Fine. So before I do that, in the last class we had seen that we had the system Ax is equal to b. We tried to solve it, we could not solve it because of certain restrictions, and therefore we had to go to the approximate solution or the best solution or the nearest solution. All those things we could do. Now the problem that we have is that we are saying that we can solve it, but the data that we get, the matrix that we get, may be a very huge size. It could be 100 by 100, 200 by 200 size, million by million, depending on what applications you are looking at. That's one thing. And the data may be incomplete. It may not have all the entries there. The entries, even if it's all of them is there, there could be some ambiguities in it, in the sense that they are not exact the way it should be. Have come, some person has just put some entry and so on, there is always data error and so on that comes into play. Fine. Further, your computing power may not be so good to take care of the things that are coming one after the other. Your calculations may not be so fast as you want, because things are changing very fast, whether you are in the stock market or you are trying to catch a thief who is running away or anything like that, where things are happening at a very fast pace. It's very difficult to keep track of things. So what you want is that you want to keep track of only few things which are important. Another example will be when you look at health, each of one have some health profile. We have some ailments and so on. So whenever you go to a doctor, he or she prescribes us that do these tests. Certain tests are done, and based on that test, the doctor decides that what ailment you have. Sometimes the doctor is successful, sometimes he is not. Fine. Similarly, there are psychological studies, there are other things to find out what are the issues, what are not the issues, and so on. Fine. So at each stage we have some data points which comes either from, say, your blood test or from your health, previous health status and so on. Or if there is a financial company who wants to try to lure you into buying certain things, then he or she will try to look at your expenditure profile, in the sense that which are the shops, which are the hotels, which are the malls that you have gone and spent how much money. They may not know actually what exactly you bought, but they will know that you have spent so much of money in certain food items or at certain places or in certain malls where these things are available and so on, and then they can try to correlate those ideas, and based on that they will try to lure you into going things. So what I am trying to say is that a person may have full information about you, a computer or somewhere it is, but it may not like to look at everything. It may just like to concentrate on only few aspects, based on which it can lure you into certain things, or it can diagnose your health issues and so on. All right. So all the data that I have may not be useful, only few things may be useful to give me approximate ideas, all right, or solutions, and hence I may not need the full matrix. So the eigenvalues and eigenvector idea is related with those ideas, in the sense that as far as we are concerned, we will study all of eigenvalues and eigenvectors, how to compute them, but it will be only few eigenvalues and eigenvectors which will be helpful in future. And not only that, when we do computational work, it turns out we need only few of them to do all the work for us. All right. So there is a notion of what is called the norm of the matrix. All right. We can divide it, then get eigenvalue 1 and then proceed and do a lot of work with that. All right. So let's try to understand some. So that was about the motivation part, that why do we need it. Some more examples where we need such things. So examples. So my question will be, I want to maximize or minimize x transpose Ax. A is n cross n, symmetric matrix, under the condition, under the constraint or condition x transpose x is 1. All right. So what I am doing here is that I have this sphere with me. So the x that I am taking are points only on this circle. All right. Fine. So I am looking at only points on the circle, and from there I want to see what is the maximum and minimum value of this. If you look at this function, all right, so this is nothing but x1, x2, xn times a11, a12, a1n, and I am assuming it is symmetrical. So, again it will be a12, a22, a2n, a1n, a2n, ann, fine, times x1, x2, xn. So, this will turn out to be equal to, if you look at, it will be summation of aij, xi, xj, I going from 1 to n, j going from 1 to n. All right, this is what it is going to look like, fine. And we need this condition that we have. So, if I want to maximize or minimize over this thing, then if you recall, there was a notion of what is called Lagrange multiplier method, all right, in our calculus several variable. So, what we do is that we form another one. So, we form a function f of x and lambda and look at x transpose ax plus lambda times or minus lambda times x transpose x minus 1. This is coming from the constraint side and this is coming from the maximum and minimum part, objective part, max min, and this is the constraint that we are looking at. And then we talk of del f by del x, we compute this, del f by del lambda, and then proceed. We compute these things and proceed, all right. So, let us try to understand what do I mean by differentiation of this. X is a vector, so I am looking at grad of this. So, let us see what it is. So, I will do it for only 2 cross 2 matrix, and from there I would like you to understand it. So, I am looking at x1, x2, it is a, b, b, d, x1, x2 plus lambda times I am looking at x transpose. So, it is x1, x2, x1, x2 minus 1, all right. I am looking at this part. So, I want to look at this function which is f of x and lambda for me. Is that okay? So, this I can rewrite it as a times x1 square plus 2b x1 x2 plus d x2 square plus lambda times x1 square plus x2 square minus 1, fine. So, now if I want to differentiate with respect to x1, I get it as 2a x1 plus 2b x2 plus, look at here, 2 lambda x1, del f by del x2, if I want to look at, it is 2b x2 x1, 2b x1, x2 goes off, plus 2d x2 plus 2 lambda x2, and del f by del lambda is x1 square plus x2 square minus 1. So, this part substituting it to be 0, all right, if I substitute this to 0, imply that constraint is satisfied, fine. If you want to write this in terms of matrix, because everything is matrix here, you can see that, look at it nicely, I can write it as, so if I want to look at del f by del x1 and del f by del x2 as a matrix, fine, I can write it as, just look at this nicely. So, 2 comes outside, a x1 plus b x2 plus lambda x1, all right. Then I get here b x1 plus d x2 plus lambda x2. So, I can write it as 2 times a b b d times x1 x2, fine, plus lambda times x1 x2. I am looking at this, fine. Or if I change it slightly, if I write it minus here, there will be a minus here, minus here, minus here, or minus here, all right. If I am doing that, or even if I am not doing it, what we are looking at is that this corresponds to looking at a x plus lambda x. I am looking at this part, fine. So, when I am looking at del f by del x, in some sense equal to 0, this gives me, I need to look at Ax plus lambda x is 0, all right, fine. So, I am putting minus here so that there is a clarity, because that is the way we are going to follow. So, if I put minus, so if we look at fx lambda as x transpose Ax minus lambda times x transpose x minus 1, then del f by del x is equal to 0 implies Ax minus lambda x should be 0, or which is same thing as saying that Ax is equal to lambda x, fine. Now, what is more important for us is that look at this constraint. This constraint says that this point x1 and x2 has to be on the circle. Since x1 and x2 are on the circle, therefore, x cannot be 0. So, with the condition that x cannot be the 0 vector, all right. So, I need to study equations of the type Ax is equal to lambda x, x is not equal to 0, fine. So, need to study Ax is equal to lambda x, x not equal to 0, where we only have information about A, all right. So, earlier we had looked at we looked at Ax is equal to B. A and B both were known in some sense for us, fine. We got exact solutions, approximate solutions and so on, but there A and B was known. Here it turns out here I want to look at Ax is equal to lambda x and x not equal to 0. If you see 0 is already a solution here, A times 0 is lambda times 0 is 0, all right. So, x is equal to 0 or the solution 0 is not the solution, 0 is not of any interest, fine. That is important, that I want solutions only which are non-zero, all right. Finally, we will see that we want only solutions which are linearly independent. So, we will see afterwards, we will look for only those solutions of Ax is equal to lambda x which are linearly independent. Fine, this is what we will look at. So, I hope you have understood what I am trying to say. I am trying to study this part Ax is equal to lambda x and try to understand what do I mean by that. So, let us take an example to proceed further. Example. So, the first example that I take is, for me A is the matrix 3 1 1 3. Suppose I look at this matrix, fine. So, as usual I want to maximize x y 3 1 1 3, x y maximize this, maximize or minimize subject to x square plus y square is equal to 1. So, this part, so if I want to write this, this is nothing but 3 times x square plus 2xy plus 3y square. I want to maximize or minimize this, fine. So, let us try to solve this part for us. So, I want to look at, so consider this system A of xy is equal to lambda of xy, xy not 0, all right, fine. Now, I do not know anything, how do I proceed? The question is that how do I proceed here, fine. I have some issues in the sense that earlier Ax equal to B was there, so I had the coefficient matrix, I had the augmented matrix, I could do it. Here I do not know the value of lambda, I do not know xy, how do I proceed? So, again system of equations comes to our hand, and here what we do is that we rewrite this as A minus lambda I of xy as 0, 0. All right. We take everything on the left hand side, and we want what we want? We want xy to be not 0. So, do you remember some theorem which talks about when do I have a system this, when does the system Bx equal to 0 has a non-trivial solution? Do you remember something about it? Here B is a 2 cross 2 matrix for us, it is a square matrix. All right, in this chapter every matrix, all our matrices will be a square matrices, I forgot to say that. So, everything here is a square matrix that I am looking at. Fine, I started with a symmetric matrix, so we have a square matrix that I am looking at. All right. So, my question is, do you remember something about when does the system this has a non-trivial solution? So, there was some comments about it in the sense that the system Ax is equal to B, where A is a square matrix, has a unique solution if and only if A was invertible. All right. So, now here I want that it has a non-trivial solution, means it should have infinite number of solutions. Fine. So, if x naught is a solution of Bx is equal to 0, then 2x naught is also a solution. Forget about 2x naught, any c times x naught, c not equal to 0 is also a solution. All right. So, we have got infinite number of solutions. So, one solution, one non-trivial solution. Solution implies infinite number of solutions. Fine. And so, let us go back. We had this, that Ax equal to B has a unique solution if and only if A was invertible or A was singular, determinant of A was not 0. Here we have infinite number of solutions, therefore, what we require is that determinant of B must be 0. So, require determinant of B should be 0. Fine. So, what do I get here? So, if I look at this example, I need, all right, A was 3 1 1 3 this minus lambda times I for identity. So, it is 1 0 0 1, determinant of this should be 0, this is what we need. Fine. So, which is same thing as looking at determinant of this matrix 3 minus lambda 1 1 3 minus lambda, determinant of this should be 0. So, determinant of this is nothing but 3 minus lambda whole square minus 1 is 0, which is same as the square of this, which is same as 3 minus lambda minus 1 into 3 minus lambda plus 1 is 0, which is same as lambda is equal to 2 or lambda is equal to 4. All right. Fine. So, understand it. Fine. So, this part tells me that determinant has to be 0. Fine. I go back and look at this part. So, the B matrix here corresponds to A minus lambda I matrix here. So, I look at the A minus lambda I, solve it, I get an equation in lambda. Fine. Since I get an equation in lambda, it was a quadratic equation here in this example because it was a 2 cross 2 matrix. In general, it could be higher. If it is n cross n, there will be polynomial of degree n and so on. So, I need to solve that polynomial. Fine. So, here my solutions were lambda equal to 2 and lambda equal to 4. I would like you to see that A times this vector 1 comma 1, which is same as 3 1 1 3 times 1 1 is equal to 4 times 1 1, and A times 1 minus 1 is equal to 3 1 1 3 times 1 minus 1 is 2 times 1 minus 1. All right. So, the one that x, y and y that we are trying to look for is also given to me. I am able to get x and y. That is because of something else that I have my experience, but let us try to compute how do I get x and y. That is the second thing, but the important thing is that given this 2 and 4, I have a solution here, all right. How do I get a solution? Let us go into that part. So, I have my A was the matrix 3 1 1 3, lambda was equal to 2, these are the two choices for lambda, fine. So, idea was to find Ax is equal to 2xy and A of xy is equal to 4 times xy. I want to solve, find solutions here, all right, solutions which are non-trivial, fine, that is more non-trivial solutions. So, the first one takes us to looking at A minus 2i of x is equal to 0. So, I am looking at this matrix, augmented matrix you want to say, or coefficient matrix, whatever you want to look at. It is 3 minus 2, A minus 2i means A minus 2i this, 1 minus 0, 1 minus 0, 3 minus 2, augmented matrix is basically this. So, I am looking at the matrix 1 1 1 1, fine. So, 0 0, which will give me the RREF of this is just this itself. This is my RREF, and this implies that the solution is x plus y is 0, implies x is equal to minus y. So, my capital X, which is x comma y, is minus y comma y. I will take out minus y outside, I get 1 minus 1, fine. Therefore, 1 minus 1 is a non-trivial solution of Ax is equal to 2 times x, fine, because I used 2 here to get my answers here. Is that okay? Fine. Similarly, if I want to go for 4, so lambda is equal to 4, if I want to do for lambda is equal to 4, I need to look at 3 minus 4, 1 minus 0, 1 minus 0, 3 minus 4, 0 0. I need to look at this augmented matrix, which is same as looking at 3 minus 1 is minus 1, 1, 1 minus 1, 0 0, which RREF is nothing but 1 minus 1, 0, 0 0 0, and from here I get that x has to be equal to y, and therefore capital X, which is small x small y, is y, which is y times 1 1, all right. So, you can check that 1 1 is a non-trivial solution of Ax is equal to 4x, fine. So, I want you to understand this part, that is very important for me. So, what exactly we have done is, so just verify it, this is what we had here, 1 1 and 1 minus 1, fine, there is no issue with that part, fine. So, what we have shown, so shown that the maximum or minimum of x transpose Ax, which was nothing but 3 times x1 square plus 2 x1 x2 I think, plus 3 y1 3 x2 square 3 x2 square under the constraint x1 square plus x2 square is equal to 1 is achieved for lambda is equal to 4 and 2, for lambda is equal to 4 and 2. This 4 corresponds to the vector x1 x2 is equal to 1 1, and this 2 corresponds to 1 and minus 1. So, just plug in the value here. So, what you get is that the maximum is for 3 times 1 square plus 2 times 1 plus 3 times 1, which is same as, so 1 into 1 and 3 square 3 3 6 2 8. So, the maximum is 8, and what is the minimum? The minimum is 3 times 1 square plus 2 times 1 into minus 1 plus 3 times minus 1 square, which is 3 plus 3 6, 6 minus 2, which is 4, all right. So, this is the minimum and the maximum value that you have obtained, Fine. Something more has also happened. I would like you to go for that part also, all right. So, as a small thing, I would just like to impress on that also. So, let us look at this thing. I want to look at, so consider all xy belonging to R2 such that xy into 3 1 1 3 times xy is equal to say 8. I want to solve this system. I want to see what is this figure. What does this curve represent? I want to understand this. Fine. So, from what I have is, you can try to understand that this will turn out to be an ellipse. All right. So, it is an ellipse. How do I see it? So, I would like to see it like this, that I have this xy with me that I have got. 3 and 1, they have some property that I will write afterwards, or let me do it here itself. So, if I look at 3 1 1 3 times this half and minus half. I should have written a square root here, but anyway. Let me write it as 1 upon a square root of 2, 1 upon a square root of 2, 1 upon a square root of 2 minus 1 upon a square root of 2. So, let us look at this part. So, this matrix is A times this is nothing but 4 times this itself, all right. So, I would like you to see that this is 1 upon root 2, 1 upon root 2 times the matrix 4 0 0 2, all right. This is what this matrix is, or I am writing A as, all right. Let me see, this is one matrix, this is the same matrix. Here it turns out they are transposed, so I would like to write it as transpose. So, I have got a matrix P transpose, diagonal matrix 4 0 0 2 times P. I am writing like this, all right. Or let me write this way, P transpose P, where P is equal to 1 upon root 2, 1 upon root 2, 1 upon root 2 minus 1 upon root 2. Let me write like this, all right, fine. So, in that case, this corresponds to looking at this time 3 1 1 3, that is A is P times. So, it is P here, all right, P 4 0 0 2 P times xy, all right. So, what is P times xy? P times xy is 1 upon root 2, 1 upon root 2, 1 upon root 2 minus 1 upon root 2 times xy, which is same as, so this into this gives me x plus y upon root 2, and the next one gives me xy upon root 2. This is what it gives me, fine. So, I would like you to see that this is nothing but 4 times x plus y upon root 2 whole square plus 2 times x minus y upon root 2 whole square, all right. Just plug in the values here, this is what you get, fine. So, from here what to say is that I am looking at all xy belonging to R2 such that 4 times x plus y upon root 2 whole square plus 2 times x minus y upon root 2 whole square is 8. I am looking at this system, is that okay? So, I am looking at this curve now. So, the curve that I was looking at is this curve itself, all right. So, you can see here now it is nothing but x plus y upon root 2 whole square upon divide by 8 here. So, 8 upon 4 I think root 2 whole square plus x minus y upon root 2 whole square divided by 8 upon 2, that is 2 square is equal to 1. So, this is the ellipse that we are looking at, ellipse with minor and major axis as what? Is it x plus y equal to 0 or x minus y is equal to 0? Which is minor, which is major? All right. So, what I am trying to say here is that somehow the study of this eigenvalues, eigenvector has also resulted in the study of what are called curves. I am able to talk about curves, and we will look at those things in the next class, all right. So, that is all for now. Thank you.